I think we should get started. Okay, well, thanks all for joining this code walkthrough talk. We are discussing about, I'll be walking through and discussing about the MDS locker. So the way I want to do this is to break it up into different series because MDS locker is a pretty vast topic with a good amount of complexity. So it's hard to kind of fit in everything in 1 hour code walkthrough. So I'll probably just split it up into like a series of 3 code walkthrough videos, covering in incremental fashion about details of the MDS locker and the code walkthrough itself. So the part 1 series, which is this, will be about understanding, why do we need an MD, why and how we need, why we need locking in the MDS. What we'll do is we'll go through different data structures involved and the way the MDS uses these structures and the locking structures. We'll do a walkthrough of some of the file operations and see how locking is used in those. And probably, discuss and walk through the code a bit about the locking itself. The next part series would be the actual implementation of the locker, which is pretty complex. And because in essence, the MDS locker is a distributed lock. You can imagine all kinds of complexities that can happen there. So part 2 series will be the implementation of the core locker itself. And part 3 will be the different types of lock classes. So the locking in MDS is divided into different classes. We have pretty simple ones and really complex ones. So and all these is kind of entangled by using state machines. So it's pretty complex. So we'll cover that in the 3rd series. So now, which is the actual, why do we need locking? Why do we need locking in the MDS? And what is locking in MDS? So we all know, why do we use locks? We use to protect anything. We use to protect state of metadata. We to mutually exclusive access to a part of storage, a part of data. So that's why we use lock. And the concept is obviously same. We protect state of metadata in the MDS in different data structures such as inode and D-entries and things like that. So why does the MDS need lock in the first place? So we all know that data managed by the MDS is pretty large. The metadata can be very huge. So it's impractical to put everything in memory in one MDS and and overload it and that will cause all kinds of scale issues. So what CephFS has is you can have multiple active MDSs. And then the metadata load is kind of shared across these MDSs. So there's a concept of a dynamic subtree partition, where a directory tree is divided into small subtrees. This is done by recording, heat of each node in the directory tree. And whenever, when a subtree is divided, so the subtree is divided when a heat for a particular node goes above a threshold value. So when a subtree is the subtree is divided, then when a subtree is divided, the node is changed from a single div fragment to multiple div fragments. And each fragment is responsible for a part of the original directory, but there'll be only one authoritative node for these fragments. So that's called the auth MDS, or authoritative for a particular directory node. Now, each MDS can bear, can bear the corresponding read and write requests for these nodes after fragmentation. So if a file is highly hot or accessed via multiple clients very frequently, the MDS will generate multiple copies of that fragment and distribute it across different MDSs. So in a sense, you can have a directory tree split because it has huge number of directory entry. So you can a single fragment will break into multiple fragments, which is called as a div frag. And then each of these fragments can potentially, depending upon the intensity of access and the heat maps, they'll be replicated, and other active MDSs will now have a copy of this particular directory fragment so that it can service read request. Now, since there are multiple clients congruently reading and writing to files, so the MDS, defines different usage rules for locking for different file metadata. So just to give an example, the UID of a file. So I'm modifying the UID of a file. That's rarely modified concurrently, right? So, kind of a shared read and an exclusive write can be guaranteed for this particular kind of metadata. Things like stats of a large directory may need to be updated by multiple clients at the same time. And this is because, this particular large directory is divided into multiple points. And different clients read and write to different shards. Shards in the sense different frags. So these shards must first ensure that they can share the read and they can share the read and also achieve simultaneous write. So it's possible that a client is updating a client is writing to one shard and the other is writing to one. So the MDS needs to ensure that the shards can share the reads and they can also achieve simultaneous writes. And only when needed, these shards data need to be aggregated to the authoritative node. So all this kind of managing clients, requests for accessing different parts of metadata requires different locking strategies and locking rules. Think of it as, we have all done, some form of, we have all written some form of code which involves locking. And say you have a particular structure, a data structure that needs to be protected from multiple access, congruent access. So we typically have a lock, right? That protects, n entries. Say you have 10 fields in that data structure, log protects these 10 fields. Now, you could probably optimize this. Say out of these 10 fields, a bunch of fields, so when you update any of these 10 fields, you need to grab the lock, update, and then unlock. That's typically how it's done. So to optimize this, what you'll do is you will have different logs covering different fields. So you can have log 1, that covers the first 2 fields, and then log 2 for the other 2 fields. That's because maybe some of these fields are infrequently updated, and maybe some of the fields are like written rarely but read very frequently. So you might have a read-write kind of log for these fields, so that you can have shared read. But for those which are like updated frequently, you will have a normal mutex for them. So we have all done these kind of optimizations and log breaking and things kind. So with MDS is the concept is more or less the same. Like for an inode or a D entry, there is not one log that protects everything in that particular for metadata held by these structures. So what the MDS does is different, have different kinds of lock types. That is one thing. Then what the MDS does is have, as I said, lock classes. So we have different kind of lock classes that have different rules for locking. So for example, we have something called as a simple lock that is like a base class implementation in typing 2. It defines the rules for the base rules for the distributed locking. Then we have kind of local lock. So you can understand local lock. It's kind of only used by an MDS because it's just used for, say, updating a version code or things like that. And then we have something called as a scatter lock, which is the complex one, which involves where you can for things like where the MDS can delegate some authority to another MDS, say a replica for a frag, so that the other MDSs can generate read capabilities for clients, and that requires the updating the state protected by them. So the scatter lock is the most complex one, and we'll see how probably not in this part series, but in the next part series how the different kind of lock classes are used. Okay, so let's see, let's see some different. So we discussed lock types, lock classes, and then we have lock states. So lock classes and lock states are kind of very much related. That's because the lock classes implement state machines, and lock states are basically just different states in the state machines. We have a lot of states, I mean, around 38 states. So that just kind of increases the complexity. But we'll come to that later, so don't worry about that now. We'll start from the beginning, which is like, the lock types. So let's see. Go to let's have, work include. Just give me a second. Just give me a second. I'll just rearrange so that I can see them properly. Is this okay? Anyone able to see emails?
Yeah, looks good.
Yep. Okay. So SRC include. Okay. So we have these different lock types. So so we have these different lock types that are used to lock different states in the metadata. So the MDS has different locks covering different portions of the fields in the inodes and the entries. So we have these defined here. What's interesting is, the way that you have to find, what these lock types cover, which metadata fields these lock types covers. It's actually, you have to go into the code. So I have kind of done that myself. So it's actually pretty evident. Some of these are very evident. Some of these are not. Like, you can say the CephLog ISNAP is kind of protect. So all of these fields, they are 13 or 14, I think 13. All of them protect the version. So, that is the base one. So let's say ISNAP, that's used to protect the snaps and the C time. Then, let's say IOTH. IOTH is like for C time, mode, UID, and the GID. Link is for the link count. Exciters, for the iExciter for the iExciter. This is for the versions. These are for the versions, and we'll see, these are like local locks. Policy is for C time, layout, quota, export pane, and they recently added ephemeral star, types. The interesting ones are the file and the nest, and these are the complex ones because these are the ones that use the scatter lock mechanism. So file is for C time, M time, A time, and dirstat. So directory statistics information is for is protected by ifile. inest is for the recursive stats. So also MDS has these recursive stats things where for a particular node you can have so yeah, there are a bunch of exciters that do this cumulative upward marking. So those are protected by inest. IDFT is for the diffractory, that is about the frags itself. Most of these locks are like simple locks, either local locks, like the versions are like just local locks. A bunch of these are just simple locks. The lock class is what I mentioned, and the ifile and inest and ifile and inest is for is the complex scatter lock that we'll probably discuss later. So these are the lock types, and we'll see, when we see the inode structure in the MDS, we'll see that, how these locks are defined. Let's do that. So MDS inode edge. So We have so what I'm not showing is these lock classes, simple lock, scatter lock. Yeah, if you go to that, we have to then understand state machines and the different lock states. That will kind of unnecessarily complicate things right now and probably confuse too. So we'll just think these are like, this is just a lock implementation. So the locker class kind of takes care of the implementation based on the lock class. So the actual, so we have a locker class that that's the locker.cc source, and that takes care of how to lock based on what type of lock class this particular lock is defined. So we have like, so you can see that, as I discussed, this is a C inode structure, and there's no one log that logs the entire metadata different from that protects the states. So we have like auth log that protects UID GID, link log, the link count, and then so forth and so on. File log is for the C time, M time, and their stats. Policy log, nest log. The complex one is for the RC, for the recursive stats. So these are the log. So we discuss log types, and then the actual C inode structure, which kind of uses these logs. And similarly, we have the CD entry. So here we only need two, like the actual log and the version log. The version log is for incrementing the CD entry versions. The interesting one is the C inode ones, because this is what is mostly used. The D entries one are pretty easy. There's no scatter log or things like that. It's just basic, either we increment, we need an exclusive log to increment the version, or just use unicycle log to for that particular D entry. Okay, so covered the log types and the inode structures. Yeah, there are other data structures that we should be looking at before we kind of to understand the whole flow of the logs better. But we'll do it on demand. Once we there are things like a log hop vector. That is a kind of a vector of logs that you fill and ask the MDS to kind of acquire those logs in a certain fashion. We'll do it on demand, and yeah, that's probably the only other thing. Let me quickly see my notes. Yep. Yeah. Yeah. Okay. Yeah. So what I'm doing with all this is, since this is really old code. Some of these sources are like written in 2009 and practically never been updated or changed. So this is really old. And these are like the most undocumented and complex part, and the most complex part of the MDS. So yeah. So what I'm doing is, just to quickly cover this, what I'm doing is, as I do this code walkthrough, there's some effort which I want to put to actually document a bunch of these things. So very simple, right? You probably know how I figured out what metadata fields these log is to go into the code. Basically here, the inode, and then go to the encode IOTH, and then see what kind of fields this log protects. So so improve some documentation, and then some of these codes, especially the locker class, is that's probably one of the most oldest code, and it doesn't use the the newer version, the newer facilities what C++ provides, and so it uses all those IRA indexing and things like that. So there's scope for improvement there, and to make it more readable. And the other thing is, once we come to these log states, they are very poorly named. I can probably not show you now, but there are names like lock and lock sync, which do not make much sense. They are not locked themselves actually, but these are like states that guard, or that that define a rule that who can actually lock, whether an auth MDS can lock or a replica is allowed to lock. So those are pretty confusing. So so as part of this, we'll probably just refactor some of it and make the code more approachable. So yeah. So back to the locking thing. Okay. So let's do some path. Let's cover some file operations and see how locker is actually used, and these different lock types and auth locks and these link locks and policy locks are used. So that will give you a feeling of how whether if you're implementing a new file operation for whatever reason, you would know. We would know that what type of logs to gather so that so that you can implement that particular file operation. Suppose that file operation wants to touch xatter, so you just need the xatter log type. So we'll see. Let's do some basic mkdir probably, and all this is tied to path traversal. So how these operations are implemented are, so we'll see, you fill in a bunch of logs and then, ask the MDS or the locker class to actually acquire a lock. So if the MDS, can't acquire a lock for whatever reason, you put it in it puts it in a queue, and later, when it can actually acquire a lock, it wakes it up, acquires lock, and then, your request is granted. And the other thing about lock is, it's kind of tied with the whole capabilities thing. So what can happen is, so for a lock request to be successful, it's also if that particular lock request needs a particular capability. Again, it's you're put on a wait queue, and then the capabilities are revoked. Probably one of the other clients has that gap, so a cap revoke is sent. Once the revoke is done, you're waken up. Then you try to acquire that lock again, and then the request is granted. So the whole thing is, and we'll see this in the state machine. The state machines also tell what kind of capabilities need to be there for this lock to be granted. Okay, so let's see. So let's quickly do handle, very basic handle client MK there. This is the server source, and this particular function is invoked when the client is trying to make a directory, create a directory. So we have these helper functions called rdlog, path, xlog entry. So quickly, so let's take an example of a client doing an mkdir. So it passes on a file path /a b c d and then say file 0. So what the MDS does is, for each of these path components, take a read log on each of these path components. So the directories from A, B, C up to D are taken. A read log is taken on these, and then the entry to be created, and there's a exclusive log taken on that. The reason for that is, the read log is taken so that it allows parallel congruent read, so that if another client is looking up this particular path itself, that can go through because it's a read log. But since if somebody is if another client is trying to modify one of these directory paths, that won't be granted because somebody already has a read log on it. So we have this rdlog path xlog entry that essentially does is, this is the one that actually goes into the locker thing. So the first thing we do is do rdlog path xlog entry. What we do is, so the interesting part, these are all some checks. The interesting part comes here. What we do is define a bunch of flags that instructs the locker class to what all to lock and and how to lock. So for a particular path, and the client doing a make directory mkdir on it, we want to RD lock each of these path components, and the actual D entry to be created needs to be exclusively locked. And what we do is we also lock the snapshots from the for each of the path component except the last component. So we'll see that. So if we happen to see something kind of a lookup, that doesn't do exclusive locks because it's just a lookup, just a get data request. It's basically mostly reading, a bunch of stuff. There's no write involved or updation involved, so there's no need of a WR lock or an exclusive lock or things like that. That is very simplistic, but here we kind of need these read locks on these path components and then exclusive lock on the entries. Okay, so let's see. And this is all kind of tied with the path traversal thing in the MDS. So path traversal is kind of implemented in MD cache where it kind of does breaks up into different path components and does a resolution. So we'll see that. Okay, so once we have these flags, we call these MD cache path traverse. So depending on the flags, we kind of assign these Boolean fields, what all we need to lock. So with RD lock path xlocked entry, we need the auth, we need to lock the snap, read lock the path, and exclusive lock the entry. So yeah, so we have the locker implementation kind of breaks the concepts into three things: RD lock, WR lock, and exclusive lock. So RD lock is shared read. WR lock is shared write. So the way WR lock is used is, for these for the file lock and nest lock. So WR lock is special and is mainly used for file lock and nest lock. So file lock is responsible for protecting statistical information in inode, which is the distrat thing, and the nest lock is responsible for protecting the recursive statistics rstat thing in inode. So all this is required since a directory can be divided into multiple shards, as we discussed, and even each shard can have multiple copies. So you could have, in order to allow the statistical information on these shards to be modified at the same time, WR lock is kind of introduced. There are scatter locks, and these are complex ones. Not really discussed right now, but that's where WR lock comes into picture. So we have RD lock, we have WR lock and X lock. RD lock shared read, WR lock is shared write. And exclusive lock is, we need exclusive access, so there's no sharing there. It's like a mutex. Okay. Okay, come here. The interesting part starts a bit below, but before that, what it does is, if you have asked to log the snapshots, we go here. There are a bunch of checks if the directory is stray and if it's deleted and things like that. We do the correct thing like return the correct terminal. So if you want to log the snap, we call into try. Okay, I should probably cover this a bit later. This try RD lock snap lock thing might confuse things. Let's do the interesting part where we actually walk the path component and try to take locks. Okay. So yeah, this is the loop that kind of, big one that does a walk on each of these components and then tries to take a log depending on which component it's in which path component it's currently accessing. So bunch of checks if it's a snap, not interesting. So we get the current directory. So for say we are doing /a, b, c, and then file 0. We are walking each of the path component a, b, c. So we come to a first, which is get the current directory c dir of a. We have some checks if we are an auth or not. The locking part starts here. That's here. Yeah. So we try to look up that particular path component. So if it's like /a, I take the so the like it's the cur data is the cur data of root, and then we try to look up a or that particular file name or a directory name, and obviously you need a snap ID if you are traversing a snap ID, but just ignore that for now. If we are able to look up, which means the entry exists, we try to lock it. So what we do is, remember that RDLock path xlocked entry, says, I want to lock each of these path components and xlock the directory entry, the last directory entry. So once we are in RDLock path, see if we want to xlock the entry, and if it's the last path component. Since there's not the last path component, we are just in the first one. We go to this part and we add an RD lock to that particular lock. So this is the directory entries lock, which we saw it in cd entry.c. This one. So one is used for locking for version. This is local lock. This is used to lock everything else except the versions. And CD entry is simple because it doesn't have a bunch of locks, protecting different fields in the metadata in the structure. It's just have locks. So you need version lock if you're incrementing the version, and for everything else, you just use the other lock. So, if you see this, we'll walk through the entire tree, the path component, and then add these and this as an RD lock. So yeah, before that, I think I just moved a bit ahead. The MDS has this lock of vector, which is defined in, I think, locker.h pop vec. Let's see. Maybe not. It's a mutation. Yeah, so lock of vector is just a vector of locks, different types of locks that you fill up and then ask the MDS to acquire these locks in a particular fashion. So we have different helpers. So we have, RD lock if you want read lock, X lock, and then WR lock. So this takes care of, when we do something like an add RD lock, it basically just puts that particular lock into a list or into this particular vector, but depending on marking it as whether it's a read lock or a write lock or an exclusive lock. So everything that needs to grab lock defines lock of vec. So you can see here, define a lock of vec and then fill it in. So while traversing the whole path component, we fill this lock of vec with different types of locks that we want. So where were we? Quickly see, I think. Hold on. Yeah. So for all the path components, we added an RD lock for the entries. And once we are in the last path component and we want to xlock the entry, which is the xlock entry is basically done for updations when we want to update a particular like creating a file or creating a directory or a symlink. So on the last path component, we add 2 locks. We add a bunch of locks like file lock. So why is this file lock required? So file lock and next lock we add as shared write locks or the WR locks. Since these are on the parent directory. So if you have like A, B, C, and then file 0, so the WR lock, so the file lock and the next lock are for the directory C. Okay, this is done since the dirstat and the rstat of this particular inode, which is the parent inode, will be modified. So once so disstat is like if you quickly see disstat. Uh, uh, up, hold on, yeah, which is like info. Hold on, where is this? INOT. I think okay. This is defined somewhere. I can't find it. Nest info T. Yeah, basically, I think it's in the INOT structure. I can't really find it right now, but it's like the rstat is protected by the nest lock and disstat by the file lock. So we need that because once you disstat is nothing but number of files and the number of directories in that particular under that particular inode, and the nest lock is like the recursive one. So we add these locks since once we create this particular directory, we are changing the number of files or the number of directories under that. So those will be modified. So we add a write lock on it. So since disstat is protected by file lock, rstat by nest lock, so add those. Then we add a read lock to auth lock for the parent for this particular D entry, for the D entry to be created. Since while creating this D entry, we need to access the parent's permission. Just like the YDGID and different other things for normal permission checks. So we add a read lock on those. Then we add an xlock on that particular final path component D entry itself. Since once we this is required, since we'll be kind of creating a new D entry, and then and then fill in the different things like linkage T, which is like the actual persistent information for that particular D entry. We can see that too. So I can see linkage T. Yeah, so since we need to fill in this linkage T, we kind of take the exclusive lock on the entry of the entry to be created, which is kind of these are the durable bits. So we take a exclusive log on that, and then once we fill all these logs in the vector. We call into these acquire logs, which is the thing that actually goes through the state machine, see if you can acquire your, you can particular log that particular metadata fields, or if it's already logged, you are put in a queue. So, yeah. So what happens is most cases, you'll find this lookup to be successful, except in the last path component, because you're mostly creating those. In that case, you'll jump to this part where you actually create a null entry, which like the lookup is a miss, and then you want to instantiate a null entry for it, and then again you do the same thing. Which is like, if you want to exclusive lock that D entry at the file lock and the nest lock for the parent inode, then add the auth lock for the parent inode for permission checks, the actual exclusive lock on the D entry itself, yeah, and then you call into acquire locks. So yeah, so yeah, this is how. So I can go into acquire logs. I'll touch it very briefly in this talk, but this is how a normal operation works like. So while implementing a particular file operation, you need to know what all different fields in the metadata for an inode is going to be touched. So if we see something like a setx header, that will just do an ix header, take a lock on that ix header, and call acquire logs. Lookup, or any other get out of call would be basically just reading information. So that probably won't that doesn't take any exclusive lock or write logs, basically just read logs. And then once everything is read, just do a lookup on, read up different fields and then return. We can quickly see. Oops. The client setx. Okay. I think, yeah. So we do an RD-log path. This is one of the other helpers, similar to, that RD-log path xlog entry, xlog the entry. This just does just a basic RD-log on everything because we really don't need. Okay, I think we probably, yeah, it just RD logs it and then it does an xlog on the xatter log itself. So it walks so this will actually just walk the path component. Let's quickly see this. Helper, I think it just calls into, yeah, just do an RD log of the path. So there's no exclusive log of the entry, just RD log the path and then RD log the snaps and then do a MD cache path traverse. So depending on the flags you pass, the MD cache path traverse modifies functions are depending on the flags you pass. So you're not passing any exclusive log of the entry. So it just does a simple read log on each of the path component. And back to here, yeah, once we have RD logged everything, we just add an xlog because we are going to modify the xatter value. So we do an add this is just like one log here. Add an exclusive log on the xatter log. The xatter log protects the version, C time, and xatters. Then we call into acquire logs. So let's see what we can do. I think if we could also do client MK node. It's, yeah, so since we are creating a new directory entry, we xlog the directory entry. And let's see if we can see if link log won't be used here, I guess. It would probably be handle client link. Let's see. Yep, the same. Yeah, there's flags such as snap and snap2, since we are kind of handling two different path components, even rename as that. So we have something called as a snap2 or path, like just like path and path2, we have snap and snap2, which is like point. Well, snap is like the snap logged will be for one particular path component. The to prefix will be for the other. So we have that notation. Let's see where we are doing. Yeah, this is a bit tricky too because now we want to log two particular paths because now we have two paths to operate on. So that becomes a bit tricky. But let's see if we can spot if we are doing some. I think it's somewhere here. Yep. Once you have taken, so I'm not going into detail into this two path xlog destination entry. It should be fairly straightforward once if you understand the normal RD log path xlog entry thing. So this it's probably straightforward too. So when we are doing a link, we are bumping up the link count. It's like the hard link thing. So we need to take a log on the. We need to bump up the link count. So we take the add an exclusive log on the link log, which link log protects the version, C time, version. Everything is if you see the encode functions in C inode source, you'll see everything encodes the inode version. So that's by default. And then the link log guards the end link, the number of links for a particular regular file. So we add that as xlog and then call acquire logs. Let's see if we can quickly do get at a. Yeah, it's I guess. Yeah, path traverse with basically nothing, so everything is like read log. Yeah, so this is mostly does. We saw the text thing, right? This mostly does read logs, and Yeah. So yeah. So this is probably needs some change. This is practically, unreadable. If you don't have all these cap notions in your head, it's basically unreadable. But you can see that most of it is just doing read locks, RD lock, RD lock, RD lock, and RD lock, because you really don't need, because you're just looking up or doing a get atta. There's no write or updation involved, so you just need RD locks, read locks. And then once that's done, the same acquire locks. Let me see if I can take you guys through locker.cc without confusing myself and everyone else. Yeah, I'll probably just defer it to the next talk. But there are a bunch of things that happen here. Like once you give a particular a vector of locks for the MDS to grab, it rearranges this. It rearranges it for, first of all, for correctness. So you can add in any order, and the locker API, which is the acquire locks interface, will rearrange it, in a particular order, and optimize it, I guess. So it does some lock merging and things like that, basically to ensure that the locks are grabbed correctly in correct order and as efficiently as possible. So, yeah, I think we'll just cover this in the subsequent talks. But, just to not to frighten anyone, these are the different lock states. So once we go into things like scatter lock, simple lock is probably the easiest one. We'll do that in the next series. The scatter locks are the most complex ones, and that uses a bunch of these states. So the main difference between the simple lock and scatter lock in terms of definition is like simple lock says simple lock says anyone can actually read lock. Sorry. Yeah, right. So simple lock is the base class that handles all these distributed locks, and the scatter lock handles locking for most complex situations. So let me see if I can define. Yeah, I think so. We'll just do this next time in the next series. I need to probably go through a bunch of these to explain you the actual differences between the simple lock and the scatter lock. So just for the sake of avoiding confusion and dragging this too long, we'll just do it next time. So yeah, and so this source is probably last tested in somewhere in 2009 and never tested again. So it's really ancient. And the logs.c source, it's a C source, not even a C++ source. So you need to duplicate a bunch of entries from CephFS underscore h, the header we just saw. We could probably make this much more cleaner so that so that it's much more approachable for people trying to make sense of the whole locking thing. So these are the state machines that is used by the locker class. So you have state machines for simple lock. Then you have state machines for the scatter lock, which is the actual distributed lock where we do share reads, share writes, and then the state machine for the file locks, which is extremely complex. So yeah. And the local lock is probably the most simplest one because it doesn't involve anything. It's just like a basic anyone can lock, anyone can read lock, but only the auth MDS can take the write locks because the auth MDS can only move the states around and increment the versions for that particular inodes. So we'll do this probably series. So I hope going through the different file operations, things have started to make sense, at least, why all these locks are required and why different types of lock types are used. And if if you get a chance to implement a new file operation, what locks to acquire. And if you're modifying the excitas, you need to take a different lock. If you're modifying the UID or the GID, take a different lock. So I hope that is clear. And I think that's mostly what I have. So I'm happy to take any questions.
Venki, so is simple lock kind of a distributed lock?
Yeah, so all these so the simple lock is the base class lock in typing and implementation. So everything is kind of a simple, a distributed lock. So it's so I'll quickly show that. If you see the simple lock thing, it says anyone can. So anyone can read lock, which is like even the replicas can read lock, but nobody can do a write lock or an exclusive lock. Does that make sense? So everything is a distributed lock. The thing is the semantics are different. So simple lock has different semantics for read, write, and exclusive, while scatter lock will have a different semantics for read, write, and exclusive, and file lock again will have different semantics for read, write, and exclusive. So yeah.
Okay. I mean, local lock isn't a distributed lock, right? From the name itself.
Yeah, right. That's only that's because it's only used for bumping up the inode and the dentry versions. So that isn't distributed. That's only locally used by that particular MDS.
The other question I had was regarding the vector of locks. So you construct a vector of locks for each FOP. Is that the concept?
Right. So everything, if you see handle client get data, everything, anything that needs to.
Yeah, because we didn't go through the code of acquire. I see that we construct a vector of locks for each FOP and pass it to that acquire function.
Right. That's what we do. So these locks are grabbed or taken or held till the scope of the request, and once the request is done, we drop all these locks. A minor point here is the MDS has something called as an early reply, where it can reply back before even it starts journaling. In that case, what happens is I think the read locks are dropped. So after the early reply, the read locks are dropped, and then once the journal hits the disk or the operation is journal, then we drop all the write and the exclusive locks. So that's a small point. Yeah, but the scope of the lock is the scope of the request itself.
Okay. No, I was just trying to understand this concept of having a vector of locks and why maintain it as a vector.
Yeah, so that's because we need different. Yeah, that's because we have different fields that need to be either read or modified for an operation. Like we saw, right? When we are creating a new D entry, like a new directory, we need to read the permissions of the parent directory for permission checks. So that requires a read lock on the parent auth lock. Then once we are creating a directory, you need to update the number of directories and stats information, like the dir stats and the R stats. So that requires a couple of other locks to be WR locked, write locked, because that needs to be updated. And then you need the snap locks for you need to protect these snaps so we take the snap locks so we read log these snap locks. So we have different, because there is no one log that guards everything, right? There are a bunch of logs. There are a bunch of logs that covers different fields in the metadata in that particular data structure, and some need to be read logged, some need to be write logged, and and to make it more complex, it could be that some of these frags are kind of are handed over to replica MDSs, and they are generating read capabilities. So to update the A time once a particular read operation is done on a particular frag, all these needs to be kind of integrated, and then the auth MDS needs to kind of update the A time. So you can imagine the complexity. That's why you need all these distributed locks and all these state machines, so that the locking is done correctly and as efficiently as possible.
Okay, yeah, thanks.
Yeah, sort of the fundamental design of CephFS is that the metadata is sharded out under different locks.
Right.
So that's and it's really quite different from most other file systems.
Yep. And that introduces a lot of complexity, a whole lot of thing. All these locking, and especially when we come to scatter locks, which are like the nest locks, the file lock, and the nest locks and file locks. And that becomes really complex, because you're just like sharding out all these metadata to replica MDSs. You not only shard, but you are actually splitting up a particular directory node into different frags, and then you can replica, you can make different copies of these frags and assign it to different MDSs. So that makes things interesting and complex. No other questions, it seems. So thanks, guys, for attending this talk. So yeah, we'll do a part 2 series. I don't know when. Probably the next slot is already taken, and probably the other one too. So we'll do a part 2 series which covers the actual acquire locks implementation. We'll go through the state machines. We'll see how simple lock works. So yeah. See you in August, guys. Thank you.